All right, so there's root x, and there's the point 30, which is not root x. Okay? Does it make sense that root x has infinitely many points? It should. They're all right there. I drew a bunch of them. Okay? If you were to pick this point here and find the distance to 30, that's what we're measuring. That's what I want. Do we agree that the distance over here looks like it should be shorter, right? Okay? Versus a point way out here, that's a much longer distance. So somewhere on this curve, there is a point where the distance from, why did that pop up again? Where the distance from the point on the curve to the point 30 is the shortest. How far, this point right here, 0, that's on the curve. How far is that from this point? Sure is 3. It's 3 away. Okay? We want to minimize the distance between the point on the curve and the point 30. So we need an equation for what we're trying to minimize, which means we're going to use an equation for distance. If only there was some equation that told me the distance between points. The derivative, you're just saying things. The distance between 2 points. Yo, it's just Pythagorean theorem, yeah. You all know where the distance formula comes from. Maybe, maybe not. It's just the Pythagorean theorem in full effect. That's the distance formula. Okay? But we gotta boil this down. First off, one point that we most definitely care about is that point right there. 30. Okay? I'm gonna call that x1, y1. So that makes my equation become x minus 3 . Are you okay with that? You don't have to call them x2 and y2 anymore if there's only x and y. Just call them x and y. Okay? Now, that's distance. Again, check this out. There's too many variables. There's an x in there. There's a y in there. We don't want that. We got to use a restriction. What's the restriction for this point? The point can move. There's lots of different points. What's the restriction for it, though? Where's it got to be? Can I just make this point? Look, that point's pretty close to there. This point's pretty close to 30. It's got to be on the curve. Thank you so much. It has to be on that curve. Okay? Which means if I told you, like way out here, the x value were 9, what do we know the y value has to be? Better be 3. Right? If I told you the x value were 2, then the y value there would have to be root 2. Okay? Now, we're not picking one of these points. We just know the point has to be on that curve. So we can't pick like an actual x value. So if I told you we were at a point where the x value were x, then y is definitely going to have to be root x. Yeah, not y. It's got to be root x. So my distance formula from a point on this curve to this point here is actually the square root of x minus 3 squared plus root x minus 0 squared. Okay? And now I have an equation that's boiled all the way down to just one variable. But before you do, so we want to drive this and find out where it's minimized, right? We want the minimum distance, the smallest distance. Before we do that, we're going to simplify this thing. Turns out that this distance formula turns into, if we square that out, it's x squared minus 6x plus 9 plus root x squared is just x. Okay? Which means my distance formula is really the square root of x squared minus 5x plus 9. And just to be really redundant of everything I'm saying today, here's what this tells me. If I told you this point here had an x value of 1, I know the y value is 1, but it doesn't matter. We can find the distance between that point and the point 30 by plugging 1 right into here. That's what that equation tells me. It tells me the distance between 30 and any point on that curve if you just tell me the x value. Okay? So what I want to do is derive that to see when the derivative is 0, because that's where the minimum distance will be at a critical value. This might seem a little cumbersome, but the derivative of a square root, we talked about this, is 1 over 2 times the square root of the same thing. If my pen works. That's just the power rule, right? times the derivative of what's inside. That's the chain rule. So that puts this on top. And all I want to know is, where is this dumb thing going to be 0? Cool. So set it equal to 0. Or undefined, technically. So it turns out the numerator is going to be 0. This is easy to see. Because to make a fraction 0, you worry, where's the numerator 0? Seriously. Okay, we need that to be 0. That turns out to be when x is 5/2. Okay, and if you make a number line for, so we can check the denominator, but the denominator in these questions are never going to be 0, because if you remember, we got this thing by taking something squared and adding something squared to it. A squared plus a squared can never be 0, unless they're both 0, which isn't going to happen. Okay, if that makes sense, good. If not, don't worry about it. The denominator doesn't matter in this particular question. X equals 5/2 is what we're looking at. If you make a number line for your derivative, and you plug in a number less than 5/2, like 1, you're going to see your derivative is negative. If you plug in a number bigger than 5/2, you're going to see your derivative is positive. What that means is the distance between the point on our curve and 3, 0 is decreasing until I get to 5/2, and then it's increasing until I get to, well, forever, it just increases. Which should make sense, right? If I keep choosing points further and further away on this curve, the distance is obviously increasing that entire time. So the closest point on that curve, the answer to my question, is when x is 5/2, which means y would be the square root of 5/2.